This one is C8H13O3Br. It has 2 double bond equivalents. We have 2 CH2 groups here, and we have a 6H, that's 2 CH3s, and another CH3 over here, so that's a total of 3 CH3s. So when you're deciding whether or not to do 2 CH3s or 3 CH2s for a 6H, look at the number of peaks, and generally what we find is this: 1, 2 or 3 peaks is generally 2 CH3s, whereas 4 peaks is generally 3 CH2s. If you'd like, you can stop the video and read about my symmetry arguments here for why this is usually the case. Looking at what we have left here, we have 3 C's, 3 O's, a Br, and 2 double bonds. So I'm thinking that we probably have 2 C double bond O's. Now we've got a C, an O, and a Br. So let's see, C, O, and Br. Everything's counted down to 0. That should be all the pieces. Now we can put it together. So we've got a CH3 here, and you can see over here we have a CH2 as well, and that CH2 is next to a CH3, and I know this because it's got 4 peaks, so 4 peaks, 3 adjacent hydrogens. Also, I know I have a CH3 that's got 3 peaks, so it must have 2 adjacent hydrogens, again proving we probably have this group involved here. Now I know we've still got some pieces here to put together. We do have some good evidence though for what goes with what. Now the 6H single peak here is probably going to be the C without any H's on it, and then the 2 CH3s connected to it like this. And what's going to happen is that these 2 CH3s will be equivalent, and they're next to something that doesn't have any hydrogens on it, so they appear as a single peak. We have a CH2 here as well to take care of, and that CH2 can't be next to this CH2 because it's a single peak. The CH2 is next to something that doesn't have any hydrogens on it, so we'll put it here for the time being. Now we do have some other things to take care of here as well. The C double bond O's. I'm going to move these over a bit. And the O and the Br. Alright, so this is actually the arrangement that we're going to use for the final structure. There's a couple of things that I know as far as the chemical shifts are concerned. If I look at the chemical shift for things that are connected to Br, you'll find that those are generally in this range. They're usually around 3.5 to 4 ppm. So what I know is that this CH2, for example, can't be attached to the Br because it's at about 2.3 ppm. It would have to be around here if it was connected to the bromine. So I'm pretty confident about where that goes. The other thing, if you look at the correlation chart, is that anything that connected to an oxygen is usually going to be around 4 ppm. So that would indicate that this oxygen can't be next to this CH2 or next to this CH2, which is why I've put it between these 2 C double bond O groups. So this here will be pretty much the only structure I can come up with that will make all of these shifts make any sense.